changing the notes. So well, I mainly just added a couple of plots that are very nice, actually. This is the plot that I did yesterday, I think, about the Ekman transport. Okay, so this is volume Ekman transport. I should share the screen. Did you share the screen for me? No. Okay, so this is, if you remember, this is Ekman mass transport, okay? It's multiplied by density. This is volume transport, so not multiplied by density, but really is the same. So you get positive, this is the meridional component. Okay? So you get a lot of Ekman flux north, forwards, both sides of the equator, okay? Which is driven by the climatological winds. And then you have this strong band of positive volume flux, Ekman volume flux. Okay? Positive meaning towards the equator. And that's due to the very strong westerlies blowing around Antarctica. Okay? And because F is negative, then the total mass transport is 90 degrees to the left, so upwards. Okay? So this is the main asymmetry in the world ocean with respect to the Ekman flux. Okay? And it's totally due to the westerlies. And that causes the upwelling in the Southern Ocean, and that closes the upper cell of the meridional equatorial circulation. So that's the new plot, one of the new plots. Okay, so we've seen what happens in terms of response to the wind stress in the upper ocean. You have zonal and meridional wind stress. You got a wind stress curl, which is what really drives the ocean circulation, as we know by now. And through an Ekman layer, that we don't care about the details, but the important thing about the Ekman layer is that it has a vertical velocity associated with it, and that vertical velocity at the base of the top Ekman layer in the ocean can be positive or negative depending on the wind stress curl. Okay? Here is negative, meaning that the wind stress curl bumps down vorticity, right? And that vertical velocity at the base of the top Ekman layer will induce a geostrophic current in the interior of the ocean. Okay? So we will start connecting the two today. Basically, this is what we're going to start to work with. Okay, so far we are here. We see what geostrophic flow is. You knew what the geostrophic flow was. Now we've seen what happens in the Ekman layer. Okay, this tiny top layer on the order of 50 to 100 meters. And if you include a curl in the wind stress of the surface, that induces vertical velocity at the base of the Ekman layer. Okay? There is a bottom Ekman layer that for now, well, maybe today we will start talking about the importance of the bottom Ekman layer as well. Okay? When you consider a simple ocean, okay? A square ocean, vertical integrated, or just a homogeneous ocean. Why don't I let please appreciate the quality of the schematic. Okay, so that is too small. So let's remember what the solutions are for the Ekman layer, for the top and the bottom Ekman layer, in terms of vertical velocity. So the vertical velocity for the top Ekman layer, we know it was 1 over rho curl of tau, rho f naught. Okay, so sorry, I should have said that what we're going to use, we're going to start with a very simple model, like that one, okay? And so it's going to be, our ocean is going to be either homogeneous, okay, or depth integrated. We will see that the solution is the same. Okay, we're not going to consider a baroclinic ocean, a stratified ocean. We're not going to do it in this class. Okay, but the qualitative solution is the same. We're going to consider for now a flat bottom. A sloping bottom will have an effect on the solution, as we will see, because if you have a sloping bottom, then you have a different vorticity balance. Okay, you have an extra term in your equations due to the sloping bottom, and that will change the vorticity balance. So that will be more realistic, and maybe if we have time, we can see the no flat bottom case. Then we will consider steady state, of course. Okay, we're not interested for now in the variability of the wind-driven jar, and we're going to use a beta plane. The beta plane that we discussed before. Okay. So this is as simple as it gets. And basically, this is it. Okay. Well, actually, there is stratified in the schematic, so that's a mistake already. Okay, so the solution for the top, for the vertical velocity at the top Ekman layer is that, so it totally depends on the Winston's curve. And the vertical velocity for the bottom Ekman layer, so at the top of the bottom Ekman layer, if you remember, depended on the divergence of the mass transport, okay, or 1 over f naught rho naught the curl of tau at the bottom. Okay, we've seen a couple of different expressions, and that, if you remember, we didn't go into the details because you were supposed to know that depended on the vorticity of the. This is the vorticity of the interior geostrophic fluid. Okay, that was the solution for the bottom Ekman layer that we didn't go into the details because I assumed that you've seen it before. But the vertical velocity at the top is proportional to the Winston's curl, and the vertical velocity at the bottom is proportional to the vorticity of the interior geostrophic flow. Okay? So the vorticity of the geostrophic flow that is above the bottom Ekman layer. That induces divergence in the transport that generates a vertical velocity. Okay? So there would be this divergence here generating a vertical velocity. Okay, so now we can start connecting all of our solutions. So start for the interior geostrophic flow. Okay, so we are here, and we start looking at our geostrophic equations. Our geostrophic equations are usual ones. Okay, the balance between the pressure gradient in Coriolis. Then we have hydrostasy for a homogeneous ocean. Okay, and then continuity. Okay, just the geostrophic momentum equations for a homogeneous ocean in which rho prime is equal to 0. Okay. So hydrostatic balance reduces to this. So we have used the homogeneous case. So rho prime is equal to 0. Flat bottom we don't know yet. Steady state we will see later. Now we can use the beta plane in this geostrophic equations. So if we use the beta plane, this is okay. And then again, Verticity. And continuity. Okay. We have simply changed the expression for f with the beta plane approximation. Now we can cross-differentiate the horizontal momentum equations. Okay. So we're going to do d by dx of this one minus d by dy of this one. So if you do the d by dx of that's f naught, so u plus d by dx of beta u plus u d by dx of beta minus 1 of rho. Okay, this is 0 already now. And d by dy of this one, so minus f naught d by dy of v minus okay, now we do one minus the other. So the pressure terms, they vanish. And so this minus that. Right. I know it's this minus this one. Okay. Okay, so is that not d by dx of u plus. Okay. Okay, so this is the y component is this one, this is the x component is this one, so this minus this. And then I have no, so many. Sorry. Well, this is a good exercise. I forgot something. I wrote down the beta plane the wrong way. So it's this. Okay. That's why it wouldn't work. Should have told me. Okay. There's a beta there. Okay, so you do it you cross differentiate d by dx of this minus d by dy of this. The pressure gradient terms, they vanish. Then we had on the left hand side d by dx plus dd by dy. Okay, where this terms here. And then we have two terms that depend on beta y that are again the du by dx plus dv by dy. Okay. I'm not going to stop again. Okay, just cross differentiating the horizontal momentum equation. But now we're on a beta plane, and in a beta plane, if you remember, beta y has to be much smaller than f naught. Right? So the changes in latitude have to be small compared to f. Okay? If it's too large, then you cannot approximate the changes in latitude in f with the beta plane. Plus PD. Okay, there's a BB here. And you cross differentiate. So, in the beta plane, if beta y is much smaller than f naught, then this term can be ignored. And so you're left with d by dx plus dv by dy plus beta b equal to 0. Okay, and if you use continuity, this is beta b which is an expression that we've seen already. Okay, but it just comes out if you use the geostrophic equations. You make the beta plane approximation, then you cross differentiate the horizontal momentum equation, and you get to this balance, which we said is actually called linear. Okay, we used the linearized equations. Geostrophic. Okay, we use the geostrophic equations. It's a vorticity balance. Okay, it's a balance between the input of vorticity and changes in planetary vorticity. So imagine, for example, that this d by dz in vertical velocity is positive, then there is a stretch in the water column. So imagine all this water column here, okay, stretches and shrinks. And so in the potential vorticity equation, that if you remember as something like this, okay, this is your potential vorticity equation. At large scales, if the water column is stretched, at large scales it will not start spinning around itself. Okay? And we will see later a scale analysis of why that is the case. So at large scales, the whole ocean will not start spinning around itself if you think about conservation of potential vorticity like Taylor columns. So this will not respond in order to conserve potential vorticity. Is f that will change. Okay. So if you have some positive input of vorticity, and for example this term is positive, then the water column will stretch and shrink. It will not start spinning, but what it will do, it will start move meridionally in order to change f. Okay. And the only thing that will do, if this is positive, it will change f so that f decreases and potential vorticity is conserved. So this is just a geostrophic vorticity balance of the large scale linear geostrophic flow. Okay, but we know, because we've seen before the solutions for the top and the bottom Ekman layer, that this is related to the wind stress. But how can we see that this is related to the wind stress? So what is the structure of the vertical shear in vertical velocity, which is the input of momentum to the ocean, which is this. That is giving vorticity to the ocean through momentum. So what is the structure of that? So I just deleted it. If you take the geostrophic momentum equations with the beta plane approximation that we're written here, and you take the vertical derivative, so we're trying to arrive to an expression for that, is minus f naught beta y, and we take the vertical derivative of the geostrophic velocity. Minus 1 over rho x z, okay? And the other one was y du dz okay, just taking the vertical derivative of the geostrophic velocity horizontal momentum equations with the beta plane approximation. But if you remember, in the geostrophic flow homogeneous, rho prime was equal to 0, and so the hydrostatic equation, which is d by dz of p, was equal to 0. So this is going to be 0, and so this implies that there is no vertical shear in the horizontal velocity, okay, because of this, okay, because the fluid is homogeneous, then the hydrostatic balance reduces to this, so these terms are equal to 0, so there's no vertical shear in the geostrophic velocity. Okay, and that makes sense. This is just a homogeneous layer of fluid in the ocean, and whatever happens to the Ekman layer that induces a vertical velocity, that will set up an interior geostrophic flow that is homogeneous throughout the layer, okay, because we're not considering a stratified ocean. So there is no vertical shear in the geostrophic velocity that this flow is inducing. And so if you use continuity, that means that this du by z is a constant. Okay? It's constant throughout the water column. So that will also be constant throughout the water column and not 0, otherwise there would not be any geostrophic flow. Okay, so now we know that there is no vertical shear in the horizontal geostrophic velocity, and the vertical shear in the vertical velocity is constant. So what is d by z of w? This is going to be the vertical velocity at the top minus the vertical velocity at the bottom, divided by h, which is the total depth of the fluid, okay, of the homogeneous fluid. And if you take the solutions of the Ekman transport, that is 1 over rho naught f naught in the beta plane, curl of tau at the top, and over h, minus the vertical velocity induced by the bottom Ekman layer. 2 over h, and then the vorticity of the interior geostrophic flow. Okay, so if you take the, you go back to your geostrophic equations, and your geostrophic equations were something like minus 1 over rho naught f naught dp by dx, and u okay, these are the geostrophic equations, the horizontal momentum. You take the derivative of this, okay, take the derivative of the geostrophic velocities, and now the solution that we had for the linear geostrophic vorticity balance is this, can be cast as, what did it do that? Okay, so now it can be written as beta b, and b, why did it take the derivative of that? I don't know. So b is dp by dx over rho naught f naught okay, now take this to the other side, so this is squared, and then I have the vertical derivative of the vertical velocity, which is that 1 over rho naught f naught h curl of tau minus d 2 over h, okay, now I see, 2 over h, and then the vorticity of the geostrophic flow, which is this, right? So rho naught f naught. Okay, now I remember why I took the derivatives here. Okay, so going back to what I did, trying to understand what the vertical derivative, this term is, the vertical derivative of the vertical velocity in the linear geostrophic vorticity balance. Okay. First we took the vertical derivative of the geostrophic flow, and we realized that in a homogeneous case d by dz of p is equal to 0, so there is no vertical shear in the geostrophic flow. Okay. And that means that this term is a constant and not 0 throughout the water column. Okay? So the solution for this term, given the solution of the Ekman layer, is vertical velocity at the top minus vertical velocity at the bottom divided by the total depth of this homogeneous ocean. Okay. And if you substitute the expressions, you get to this. Okay. Now you go back to your vorticity balance equation. Okay. Beta v, beta V, you substitute it with the geostrophic velocity, divided by F naught, and then you substitute what this term is, which is this, okay? 1 over rho naught F naught H of the curl of the wind stress, minus the solution of the bottom Ekman layer, which is the vorticity of the geostrophic flow. And with the vorticity of the geostrophic flow, you can put it in terms of pressure by taking the derivative of the geostrophic flow, and you put it here. Yes? Maybe? So you get rid of this, you get rid of this. So you have beta dP by dx is equal of the curl of the wind over the total depth. Must be F naught. Yes. Minus the practice. Minus d over 2 fraction of p. Okay. So this is another way of looking at this vorticity balance. So basically what this equation is telling us is that on the right hand side you have the solution of the Ekman at top and the solution of Ekman at bottom. Okay? Ekman at top is given by the wind stress curl. The one at the bottom is given by the Laplacian pressure, which is the geostrophic pressure. Right? This vorticity in the geostrophic flow. And that will induce a meridional velocity. Ekman at top, and this is Ekman at bottom. Okay. So this is how you can start putting together the solution of the top and bottom Ekman layer with the induced interior geostrophic flow given by the wind stress, and then eventually we will see drag at the bottom, okay, given by the bottom Ekman layer. So this is a typical, very simple first model of the wind-driven circulation. And we have assumed a homogeneous ocean, flat bottom, of course. Okay. In a no flat bottom case, there will be a different pressure term here. Steady state, beta plane. Okay. So if we were on a F plane with F constant, so no beta, there will be no vertical velocity induced. So if you remember the geostrophic velocities with a constant F, they had no vertical velocity, right, associated. When you introduce beta in the geostrophic equations, then you have a vertical velocity. And that, so beta allows you to have a vertical velocity and to have a shear in the vertical velocity. And because of that shear in the vertical velocity, you can generate an interior geostrophic flow, a meridional geostrophic flow. Okay? So this very simple first way of looking at the interior response to the wind stress. Okay, this is a typical forced dissipative system. Okay, you're forcing at the top, and you're dissipating. We will see we are dissipating at the bottom Ekman layer in some way. Okay, so this is relatively simple because it's the wind stress. Okay, so this term is simple. This term depends on how you put it. You can put it in different ways. Okay, we will see a couple of them, and also Actually, you could start thinking that in a real case, okay, this is a very simplified model, but in a real case, the wind influence doesn't reach the bottom, of course, right? So it's very hard to believe that the momentum, that the input of momentum or vorticity is dissipated at the bottom by the bottom Ekman layer with this step. Okay, so there must be another way of dissipating the input of vorticity that is not at the bottom, because it's not going to go all the way through the bottom, because it's not homogeneous. So we will see that there is another way of dissipating this input of vorticity that is with lateral friction. Okay, so momentum will not be dissipated at the bottom, but it will be dissipated with lateral friction, either on the west or on the east. And I guess you know the answer already. Okay, so if you don't well, now we can move on. So now that we know that this is a force dissipative system and there is a wind stress at the top that is imparting vorticity, and this vorticity will have to be dissipated somewhere. So, well, yes, I can show it to you. So this is the typical Verge of Balance, okay, that we will see at least 3 times. So it's a balance between the input of vorticity at the top by the wind stress and the change in vorticity by planetary vorticity. Okay. It's called Verge of Balance because this person called Verge first arrived at this expression. Okay. But this is not enough, okay, because if you just substitute, as we did I think the last time, this with the wind stress curl, just with the top solution, of course you're not dissipating the input of momentum or vorticity, okay? So it's not a balanced flow. And then if you actually look at the solution, there is something missing. Okay. This is, we will see how I try to compute this. But this is what you get if you just use Verge of Balance. Okay. So if you just use Verge of Balance and you say, okay, I have, if we're looking from the top now, if we're looking from the top, so this is north and south, this is east and west, okay. I have a wind stress curl. Let's imagine the subtropical latitudes. I have a wind stress curl that is giving me a negative vertical velocity. So into the board. That will generate a vertical velocity into the ocean, like the schematic that I showed before. And with that, the interior of the ocean will respond by changing planetary vorticity. Okay, so eta, which is nothing but change in planetary vorticity. So you are squashing down the layer. Come in. No? Huh? There's the wind. Okay. So you're squashing down.
Trying to attend the lecture.
Yeah. The wind stress is the wind. So the wind stress in this case is squashing down the full homogeneous layer of the ocean. Right? So it's generating this constant vertical velocity. And so you're squashing down the full water column. And you're not going to start spinning by yourself, but you're going to change your planetary vorticity. And so you will change planetary vorticity in order to reduce beta and conserve planetary vorticity. And so you will go towards smaller values of f, so you will change your beta, and so you will go towards the equator. This is north. I guess you've seen in the first part of this course all the different cases of, you're shrinking, you're starting to spin faster, or, I think the typical examples of is somebody texting during the lecture? Plop, plop, plop. Okay, so you can, if you change relative vorticity, you can either change planetary vorticity or shrink or stretch and blah blah blah, all the different cases. Okay. In a large scale flow, this is not going to help you to conserve potential vorticity at large scales. Okay, the whole ocean will not start spinning around. So it will either. So if this changes, this will have to change accordingly in order to conserve planetary vorticity. So if you're squashing down the full water column and H decreases, F will have to decrease as well. And so the whole homogeneous layer of this ocean that I was showing before will start to move towards the equator. Okay. So this is basically the response in this Verge of Balance. Okay. So we have this input of vorticity, and by conservation of potential vorticity, beta changes. And in the case of a subtropical gyre, then the whole interior geostrophic flow, this is a V geostrophic, okay? The whole geostrophic flow, there will be a geostrophic flow generated by this input of vorticity that is a meridional component. And in the case of a subtropical gyre, it will go towards the equator. Obviously, there's no conservation of momentum here because you cannot imagine an ocean that is all homogeneously going in one direction, and there's no return flow to conserve mass, to conserve momentum. Okay, so there's something missing here, of course, in this Verge of Balance. And actually, if you compute, we will see later how, but if you compute a Verge of string function, okay, you can go from here, you can define a string function. Okay. And compute the string function from just with the wind stress curl, okay, the same wind stress curl that I've been showing you all of this time. Okay, this one. So I just took the North Atlantic and the North Pacific regions. I took the wind stress curl, beta, defined a string function, and then you have to integrate zonally. Okay? So you have to integrate zonally this string function from x east to x west, your geostrophic velocity, or from west to east. Okay? And you have to define one boundary condition of no normal flow, so v equal to 0. So you could choose, as we will see later, you could choose the boundary condition to be on this side east or on this side west. Okay, mathematically, they're both valid. Okay, you can define your boundary condition of psi equals 0 on the west and start integrating zonally, or you can put your boundary condition of psi equals 0 on the east and integrate zonally. The result is the same, is a meridional velocity geostrophic flow that goes towards the equator. Okay. So here I decided to put the boundary condition on the east, okay, of course, and integrate zonally. Then what you get is this line of, these black lines are the constant lines of string function. Okay. This is the North Atlantic, this is the North Pacific. I didn't put the mask yet, but anyway, here you can see Florida, this is America, there is Spain and Africa here, this is Japan, and this is California. So what you see in that case is that if you put the boundary condition on the east, then you get streamlines that are like this. And what is happening to the flow, of course, within the streamlines is flow that is going towards the equator. Okay. I could have done the opposite. I could have put the boundary condition on the west, okay, mathematically is valid. And I would have had the same meridional flow towards the equator with the same magnitude and the same direction, okay? But the stream function, so the direction of the flow would have been the opposite. So mathematically they're both valid, but physically there's only one that is valid and realistic, of course. So this qualitatively is actually, I mean, it's amazing if you think about it, that if you just have wind and you compute wind stress and you compute the curl, you can get the transport of the interior of the ocean away from the boundaries qualitatively right. So qualitatively about 40 to 50 Sverdrups for the interior of the ocean is qualitatively okay. I mean, it's not right, but it's not bad, given that your only input is the wind stress curl. Right? Of course, this is a homogeneous ocean, so this is telling you that the whole North Atlantic and the whole North Pacific is behaving like this, which is not true. Okay, the response is just the upper ocean, so down the main thermocline, 1,000 meters or so. But if you take this very, very simplified model, which is just a couple of equations, and you reduce it to this, and you just need to know the wind stress and compute the curl, then you can get the transport of the wind-driven gyres quite okay. Once we will see the full solution, that is quite realistic, you will see that this is actually not bad. Okay, so this is what is happening in the interior of the wind-driven gyre. Okay. This is okay. What is totally wrong is once you try to close the contours, the lines of a constant stream function, the streamlines. Okay, these are hitting the continents. So we will need a boundary condition, another boundary condition, either here or here, to close the streamlines. Okay, and that is what is missing. So basically, this Verge of Balance is a very good solution for the interior of the flow, but it's not a good solution for the boundary flow. We will need a return flow to return all of this mass that is going towards the equator. Okay? And that boundary current will be either on the west or on the east. It could be on the west or on the east, as long as it allows the flow to conserve mass. Okay? So what we'll do is, at some point we will have a full solution, okay? And the full solution for the wind-driven gyre, the stream function for the wind-driven gyre, will be a stream function given by this Verge of Balance, okay, that will describe the interior of the wind-driven gyre, plus a stream function for the boundary. Okay? And once you put the two together, then you will have the full solution of the wind-driven gyre. So far as Verge of Balance, which is not bad for the interior of the gyre. So for the interior of the gyre, if you just consider this, and qualitatively it is not bad. Okay. So after Sverdrup, Stommel arrived, very famous oceanographer, and said, okay, Sverdrup balance is fine, but Sverdrup balance, there's no dissipation in Sverdrup balance, okay? And there's no return flow. So he went back to this equation and he said, okay, this is the wind stress curl, what is this term? That is the dissipative term in my simple model. So let's see what the Stommel model is. Okay, so Stommel started with the Geostrophic equations. We're going to write them in a slightly different way, but it's always the same. Momentum equations. Okay. So we are defining phi is pressure over rho naught, and buoyancy is minus g rho prime over rho naught. Okay. So these are the horizontal momentum equations in one. And then we have hydrostatic balance, and we have continuity. Okay, so here we have used the geostrophic momentum equations, and we have retained the frictional term as before. Okay, so these are the two horizontal momentum equations, okay? And we can again cross-differentiate them. So this is one. If you cross differentiate one, what you get curl of top over rho naught. Okay. If you just cross differentiate the zonal and meridional components of the horizontal momentum equations. Okay, so he started from the same set of equations, geostrophic equation with the frictional term, cross differentiate the horizontal momentum equation, and now take again. We started the homogeneous, now take a depth integrated ocean, okay, which is basically the same thing. So you integrate over the full depth of the ocean. So you integrate from the surface to the bottom. This is going to be the curl of tau at the top minus the curl of tau at the bottom. Okay. So you're just integrating from the surface to h, the full depth of the ocean. This, remember, this is our set of equations, geostrophic equations, with the hydrostatic balance and continuity. Okay? So this, because of continuity, this vanishes. And so you're left again with beta V, and V bar is the vertically integrated meridional velocity. Curl of, not tau at the top minus tau at the bottom. So obviously he arrived to the same conclusions that we saw before. But now what the real difference in the Stommel model or Stommel problem is what he did with the dissipative term at the bottom. Okay. So he said this is my meridional geostrophic flow vertically integrated over the full depth that is resulting from the input of vorticity. This is going to be, of course, my curl of the wind stress at the top. Okay. And then what he did for the bottom term, which was that Laplacian of pressure, that is the effect of the bottom Ekman layer, he parameterized with a linear drag. Okay. So he parameterized the effect of the bottom linear and bottom Ekman layer with a linear drag, okay, in order to dissipate the input of momentum. And he parameterized that in this way, R and the vorticity of the geostrophic flow. If you remember, the solution for the bottom Ekman layer was proportional to the vorticity of the geostrophic flow and the depth of the Ekman layer. So, because the vorticity of the geostrophic flow is unknown, he parameterized that bottom term with a linear drag or Rayleigh friction. So this is your linear drag coefficient. Okay, totally arbitrary. And this is, of course, the vorticity of the interior geostrophic flow, right? Vertically integrated as the meridional flow induced by that. Okay, so this is really the difference between this Verge of Balance and the first model that considers, okay, this Verge of Balance is telling me that there is an input of vorticity by the wind stress curve that sets up in motion a meridional velocity, but what happens to the other term of the bottom Ekman layer, which is the forced dissipative, the dissipated part of the system, okay? So how can I dissipate this input of vorticity? First approximation is, okay, I have a bottom Ekman layer, I will approximate the effect of the bottom Ekman layer with a linear drag. Okay, so that will dissipate my input of vorticity. And so very simple way of parameterizing that, because the solution of the bottom Ekman layer is proportional to the vorticity of the geostrophic flow, it's going to be the vorticity of the geostrophic flow times some linear drag. Now the velocity is divergent free, okay, in this set of equations. So I can define a stream function I can define a stream function that satisfies continuity. And if I substitute this stream function into the solution of the Stommel model, then I get beta my vertically integrated meridional velocity. And then it's going to be the curl of the wind stress minus your linear drag. And then if you substitute the vorticity of the geostrophic flow with the stream function, then you get the Laplacian of the stream function. Okay. And this is really this Thomas solution. What is different from Verge of Balance is this, right? An input of wind stress curl, vorticity by the wind stress curl, and a meridional velocity associated. Stommel added linear drag at the bottom. Of course, it's not realistic. Okay. In the real ocean, the input of vorticity by the wind stress cannot be dissipated at the bottom of the ocean at 5,000 meters. Okay. But this is a first approximation in this very simple model: homogeneous, flat bottom, steady state, and beta plane. Okay. You can arrive to the same conclusion using potential vorticity conservation. And we will see that by using the potential vorticity conservation, we will understand, doing a scale analysis, where friction should be. Okay. So we just did a depth integrated model for the Stommel. Okay. We can go back to the homogeneous model and look at the potential vorticity conservation. And your potential vorticity equation is this, and if you add a forcing to your equation, it's going to be this, your potential vorticity equation, okay? Where h is the total depth of this homogeneous model, and f is forcing and friction, so it could be both of these terms, okay? Whatever forcing agent, forcing or dissipating. So if the ocean is flat at the bottom, okay, and you work out these terms with h constant, then you're left with this for a flat ocean. Okay. If you look at the Lagrangian derivative for h constant, you're left with them. And this is the barotropic PV equation that you might have seen with Fred. Barotropic PV equation. So again, the flow is not divergent if you assume vertical velocity equals 0 at the top and bottom. And so you can define again a stream function. And if you define again a stream function, the same way we did here, and you put the stream function here in the vorticity term and in the beta term, then you arrive to this plus beta, the meridional geostrophic flow, and then some f, which is due to tau. Okay, the forcing of the wind stress curl minus the dissipative term, which is this. Okay, because I chose the forcing term to be like this. So this is, as you can see, the same Stommel model, but now includes time dependency and nonlinearities in the Lagrangian derivative. so this is the full, okay, if you actually want to integrate in a numerical model the full Stommel solution, then you take the time derivative as well, so the time dependency, and all the nonlinearities in the term. So you would like to work with this equation rather than this. Okay. This is the linearized, time-independent solution of Stommel. This is the full solution of Stommel. If you take the steady solution, okay, so the d by dt is equal to 0 there, you can arrive to expression like this, which is the Jacobian plus eta and then rho minus r. So here you have the nonlinear terms inside of the Jacobian. This is just a steady solution. If you also remove the nonlinear terms, then you recover the steady linear solution of Stommel, of course. Okay. So we basically arrive to the Stommel problem in 3 steps using the potential vorticity conservation. Now, if you take the barotropic PV, you can start making some scale analysis that can be useful. Okay. So take the barotropic PV, and you make a scale analysis. So this is U over L, some typical length scale and some typical velocity. And then beta V is beta U, okay? Some typical velocity and beta. And they're equal to F. So you can write this as U over L, and then beta L. Yes. Okay. And I can define Z as U over L, so a typical value for vorticity. So if I want to ignore the nonlinearities, okay, these nonlinearities, then Z, which is this, should be much smaller than beta L. Okay, so that these terms can be neglected, and I'm left with the this. Okay. So Z, the vorticity, should be much smaller than beta L in order for nonlinearities to be neglected. Or in other terms, you can write, you start from here, you get U over L squared beta should be much smaller than 1 for nonlinearities to be neglected. And this is actually called the beta Rossby number. This is the beta Rossby number. And so assuming the beta Rossby number to be much smaller than 1 is the same thing as assuming that nonlinearities are small and can be neglected. So we will see that the beta Rossby number is much smaller than 1 in the interior of the ocean, so nonlinearities can be neglected, and you are left with a balance between the wind stress curl and planetary vorticities. But close to the bottom, or close to the sides, where you have lateral friction, nonlinearities are important. Okay? So the beta Rossby number is roughly 1. and so non-linearities have to be included. For example, in this case, linear drug. How much time do we have? 15 minutes. So we take the Stommel model that we have seen that it can include time dependency, non-linearities, and has a parameterization for the bottom Ekman layer. But now let's not think about time dependencies and non-linearities in the flow. And so we go back to the steady linear solution of Stommel, which is this one. So I don't want to start this because I'm not going to be able to finish it. So we'll do it the next time. But I can show you something. So now what we're going to do with the Stommel model is find a solution for the interior flow, which is going to be Verge of Balance, not surprisingly. Okay, so in the interior flow we will neglect non-linearities and frictional terms, so this term will go away, and we will be left with a balance between Winston's curl and beta, and that is this Verge of Balance, and that will give me the interior solution. And then we will have a solution for the boundary layer that includes non-linearities. So in some other places, non-linearities will be important and will be kept, and that will be the solution for the boundary layer. Well, in this case, the boundary layer is at the bottom. And then you have to put together the two solutions, and you get the solution for the Stommel model. But it takes more than 7 minutes, so I don't want to stop. But I can show you something in order to finish on a good note. I want to show you where we are going. Okay, what we're going is trying to find a solution with a simple model. Okay, eventually we will, I don't know if we will be able to include the effect of a sloping bottom, but if you include the effect of a sloping bottom, then you include non-linearities on one side. We will see which one. Eventually you get, with an analytical model, very good solution of the wind-driven gyre. Okay? And so we will get a solution that looks something like this for a subtropical ocean. Okay? So we will have an interior solution, which is going to be this Verge of Balance, okay? And then a solution for the boundary current. That will be on the west, but you know this already, so I'm not spoiling anything. Could have been on the east mathematically, but it's actually on the west because of conservation of potential verticity. And once we put them together, then we get the full solution of the Stommel or Munk model. Okay. And that is going to be simple in this square model, in this squared ocean, where you can actually put it in a realistic geometry and get a very nice description of the wind-driven gyres. And eventually the description of the wind-driven gyres is what we're trying to approach is a solution that comes from at least a numerical model. Okay, and this is a couple ocean atmosphere model that is of high resolution. High resolution in the ocean means 10th of a degree. Okay, this is super high resolution in an ocean model. Okay, because it's very expensive. And if you reach 1/10 of a degree, you're almost resolving if you remember, you're almost resolving the Rossby radius up to 40-45 degrees north and south. Okay, so it's quite good already. So you're resolving mesoscaletes in the ocean at least up to 40 degrees north and south. And you are resolving the Rossby radius, also the beta Rossby radius, and so you get a better solution of also western boundary currents. So 1/10 of a degree is roughly the size of Manhattan, and it's still very big for an atmospheric model, but in the ocean is super high resolution. And this is basically all the 1/10 of a degree grid cells that are covering the ocean surface. And once you take the primitive equations and all the equations that you know, and you start integrating your ocean model, eventually what you get is this, 1/10 of a degree ocean model. Now what you're seeing here is what we are trying to, where we're trying to get with this simple model. What you're seeing here is a western boundary current, very warm western boundary current, that is flowing northwards, and then is closing this wind-driven jar. And we will see that this western boundary current has to be very strong to conserve mass, and is actually very narrow. You see that this Gulf Stream is very narrow. It's very narrow also because this boundary layer is very narrow, because it's a frictional boundary layer and it's very narrow. And in that narrow boundary layer, all this flow that is flowing equatorward because of this Verge of Balance has to return northward to conserve mass. So it's a very fast, there's a lot of volume of water flowing northward in this tiny Gulf Stream western boundary current. And you see that the linear time-dependent problem is good to qualitatively describe what is going on in the wind-driven jar and the western boundary current. But this western boundary current and this wind-driven jar is definitely not time-independent, and is definitely not linear. You see all these filaments and eddies that are detached from the western boundary current, and all these structures that are on the sub-mesoscale. Which is definitely not linear, and is definitely not steady. Right? So whatever we're going to do is a very crude approximation of what the reality is, and this is not even reality, of course. But eventually, with these simple models, there are this Verge of Balance, the Stommel model, and then the Munk model, which is the one that is getting closer. It's a good approximation. It actually gives you the width of the boundary current. It gives you the qualitative structure, so it puts a boundary current on the west. It conserves potential vorticity, and it gives you a very good indication of what the main characteristics are of the wind-driven jar. But obviously it doesn't get to this nonlinear time-dependent solution. And then you can spend hours watching this video. These are tropical instability waves at the equator. And then you can see equatorial upwelling. And this is another western boundary current, right? The Kuroshio. The Kuroshio is flowing next to Japan and China. And it's closing the North Pacific wind-driven jar. Okay, so this is the solution. This is the solution that gets closer to reality, and this is the integration of this Verge of Balance, right, in the North Pacific. So far from reality. But actually, if you look at if you were able to look at the transport, this is about 40 Sverdrup maximum in the interior. If you had to compute the transport in this model in the North Pacific, it will not be very far from 40 Sverdrups. Okay, so Verge of Balance gives you qualitatively the good answer, because it all depends on the Mister's curve. It doesn't give you a western boundary current, doesn't give you the details, but the main features are there. And this is just beautiful. See, these are the isosceletes that detach from the Agalas current, the interaction between the Agalas current and the circumpolar current. There are mesosceletes that detach and they start flowing into the Atlantic Ocean. And this model barely resolves them. But you can see, in a 1-degree model, you wouldn't see anything. You would see just laminar flow going into the ACC and no eddies going into the Atlantic Ocean. Here you can see an Atlantic Nino. You can see storms and tropical cyclones passing by. Did you notice? There was a storm passing by. Anyway, I can share the video if you like. Okay, so I'll see you on Wednesday, and we'll go on with the Stommel and the Monk model and find the solution for the interior and the boundary current.